So yesterday we defined a pretty simple example of cohomological quantum field theory in 0 dimensions using an analogy to differential forms. If you remember, you take some bosonic fields, you describe coordinates on your manifold, and define a BRST symmetry that maps them to some other fermionic coordinates. And then maps these fermionic coordinates to 0. And we observe that the typical observable, which is some function of x and c, can be interpreted as differential form. Simply by replacing the c's with the x's. And that the BRST symmetry is just the usual differential for differential forms. Now, I mentioned that differential forms can be integrated on the whole manifold or on submanifolds. So suppose that there is some submanifold inside my manifold, defined by a bunch of equations. If I want to integrate a form of degree d minus k on this submanifold, all I need to do is to integrate on the whole manifold f, sorry, bad name, let me call this omega. Omega wedge the product of dfa delta of fa. So the delta function will force me to live on the submanifold. And this prefactor will make sure that the answer is actually independent of how I parameterize the submanifold. So you can easily check that if you replace this function with some linear combination of this function, some other collection of functions which define the same manifold, this answer would not change. Because the delta functions will, when you transform the arguments of the delta function, you'll generate some Jacobians that cancel out against that. Now, there is a convenient way to write the combination dfa delta of fa. You can do a Fourier transform to represent the delta function as an integral against some auxiliary variable. And then it's convenient to do things in a symmetric way, to also sort of Fourier transform this df. Sort of introduce a fermionic variable. And write something like this. So when you do this integral, you just pull down a b. You get the f. You do this integral, you just get the delta function in f. So going back here, we can think about path integrals of this form, where I have an integral over dx, so just dx, dc, db, d capital B, the little b. So this is bosonic, this is fermionic. And then I can put sort of an action and then some observables. So this integral will represent the integral of these forms over the submanifold defined by the fi equal to zeros. Fa equal to zeros. This formulation is nice because this still has a BRST symmetry. It maps little b to capital B, and it maps capital B to 0. Let's check that this is true. when I act with Q on this expression, right, I get B dFc. When I act on this expression, I get capital B dFc, which cancels the previous one. And I get, sorry, I should put an I here or something like that. Maybe even minus sign. And then I can act here. I get something like B second derivative of f cc. That gives 0 because of antisymmetry. Because we are antisymmetrizing the second derivative. It's a simple exercise. Another way to verify that this is sort of invariant under the action of Q is to notice that this combination can be written as Q of BA FA. So clearly it's annihilated by Q. Okay? Only minus. Now, this sort of integrals have a nice property. If the forms are closed, this integral is actually independent of small deformations of n. So if I integrate on some submanifold or a nearby submanifold, the answer is the same. So and also this integral does not change if I shift omega by an exact form. So remember, we were saying yesterday that the cohomology, so closed form modulo exact forms, captures topological information about the manifold. One manifestation of this fact is that the cohomology can be paired with submanifolds in a way that is independent of small deformations of the submanifolds. In this setup, this follows from the fact that if I deform my f's, my action is changing by Q exact term. And so the correlation functions do not change. So, like in the most extreme case, I can put as many constraints as the dimension of my manifold. Right? I can put as many B's as C's. Then, what this is doing is just sort of, so this collection of F's will identify a bunch of points on my manifold. This integral is sort of counting those points or summing over those points with signs. I mean, let me just give a very, I don't know if it's what, anyway, I don't think there is. Well, okay, let me just consider a very simple example. Suppose integrating of minus infinity to infinity is sort of df over dx delta of f of x. What's the value of this integral? Which points, which values of x give a contribution to this integral? The zeros of f. What's the contribution of each zero of f? So the delta function gives me 1 over derivative of f. Then I'm 1 over absolute value of derivative of f, right? And then I'm multiplying by the derivative of f. So this gives me a sum over the set of solutions of f of x equal to 0, right? Of the sine of df over the sine of df over dx. So let's draw a picture. suppose I look at a function which starts very negative and ends up very positive. The number of intersection points, well, here there are 3 intersection points, but this contributes 1, minus 1, 1. The total is 1. If I look at a different function, we just did that, I would have just gotten a single contribution. No matter how I deform my function, as long as I don't mess up things at infinity, the answer is going to be constant.
What happens for quadratic or higher order groups?
Then you get a more complicated expression, but you can perturb a little bit. But yeah, the answer is going to be the same. They will count as in the same way as the number of simple roots you get by deforming the problem a little bit. So here, this is just count. Essentially, this integral is checking if you're going to, if you end at positive infinity with the same sign as you were starting at negative infinity. Okay, so this is sort of a very simple topological invariant property of this function. Does it cross the real axis or not? Okay. So, right, so here in this setup, I had as many C's as X's. I was sort of trying to make the whole manifold topological. In the gauge theory setup, we only want to make the gauge orbits topological. We want to sort of, while keeping the rest of my space of configurations in full. So instead of introducing a C for each coordinate of my manifold, we only want to introduce C's associated to the action of the gauge group. So suppose that I have some manifold and has some action of G, of a Lie group G on it. I'm going to take X's, which are coordinates on the manifold, and I'm going to get ghosts which belong to the Lie algebra of the group. So my BRST transformations now. So the group, how does the group act on the manifold? It acts by vector fields, right? If I have an infinitesimal action of the group, it will move each point by some amount. This amount is a vector field, right? So to each generators of the group, of the Lie algebra, I'm going to associate some vector field. Sorry. Let me put it down. So in particular, if I want to sort of cancel the directions that correspond to these vector fields, I'm going to introduce ghosts and a BRST transformation with maps X to the vector field. So the ghost, essentially the BRST transformation acting on the bosonic variables is the same as a gauge transformation whose parameter is the ghost. Then I want to q square of x to be 0. So when I act on these, I get sort of q of CA, VAI, plus, actually minus because of Grassmann odd, CA, q of these, which is DJ, which is VJBA, sorry, VIJB, CB. right? I'm just applying Leibniz rule. And then because this is Grassmann odd, I can anti-symmetrize this. Now this expression is called the Lie bracket of two vector fields. It's the answer to the question, what happens if I first move in this direction and then in the other, or vice versa, minus the opposite. Like when I'm on a sphere, if I'm rotating a sphere, I can say I rotate it first infinitesimally like that, and then infinitesimally like that, and then I subtract off the opposite order. So I rotate first like this, and then like this. Right? It's the commutator of two group actions.
I don't understand how you get the second factor of phi.
Well, I'm using this, right? Yeah. This means that when I transform any function of x, this is Ca VAI df over dxi. So I just applied it to this v. Okay. So the commutator of two symmetries is still a symmetry. So whenever I have these vector fields, it must be the case that this sort of Lie bracket is a linear combination of the original vector fields. So these are the structural constants of a group. For example, if I have a group of rotations, right? If this is rotation around the axis 1, and this is rotation around the axis 2, here you will find rotation around the axis 3, right? The commutation relations of SO3. Mm-hmm.
Sorry, I don't understand why we chose Q to cancel the effect of the action of the group to begin with.
I'm just saying, let me just do this. The intuitive motivation for doing this is that ultimately I want to have a technology which allows me to ignore, to have this G act as a gauge group. So to identify configurations related by the action of G. So here I saw that these gauss were canceling the whole of the axis, right? Mm-hmm. If I had if I only want to cancel some directions, I will have to use C's which point in the same directions, right? For example, suppose that I change coordinates, right? I write my x's as x's of x primes. Some function some x primes. Then q of x is written as c prime, right? Dx over dx prime. Right? Now, suppose I only want to make topological the first coordinate here, x prime 1. Then I will only introduce one ghost corresponding to the direction 1. Okay. So this is just this is the vector field corresponding to a small change in x1. And so I have it here. So the only difference on what I was doing there and what I'm doing here is that here the vector fields d over dx1, x prime 1, say, and d over dx prime 2 commute. Here I want to have a slightly more general situation where these vector fields might not commute, but they're still, the commutator is still a linear combination of them. So where I have structural constants. So here I get something like minus CA, CB, F, AB, C, C of V, I, C. So you can see that in order to cancel it, I need to define the transformation of the ghosts as the following. So I need to put the structure constants in the transformation of the ghosts. Now you might want to check the q square of C is 0. So you're going to get something like F, F, C, 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 with a bunch of indices like A, B, D, B, C, C, D, E, B, D, E. Right? Now, again, there is an antisymmetry. Let me just put a C here. There is an antisymmetry with these three indices. I get sort of this antisymmetrization of this product of two Fs. But this vanishes because of Jacobi identities. But I just take an expression like this. I look at VA commutator of VB, VC. You know that this satisfies Jacobi identities. So antisymmetrizing these letters gives me 0. And that's that. So this is a self-consistent thing. So this setup allows me to discuss integrals over the space of orbits of G in terms of integrals over the whole manifold of certain observables which are functions of X and C's. And I can still introduce this sort of other degrees of freedom in order to impose constraints. For example, if I want to gauge fix my problem completely or in part, I'm going to impose a bunch of equations which sort of cut each orbit in a bunch of points. And then a path integral like integral over X, C, B, and B of an action of this form is going to sort of, so let me make a picture. Suppose this is the manifold. These are the gauge orbits. My F's define some constraints. So this integral will essentially evaluate an integral over these constraints, counting each intersection point with a sign, so that if my constraint happens to go wrong a bit, do something like that, it's not a big deal. As long as the net number of intersection with the orbits is, say, 1, everything will be fine. The same way as this was giving me 1, no matter how many times my function actually wiggles. And the answer is also going to be independent under small deformations of these Fs. So as long as you have a BRST symmetry, and this BRST symmetry remains nilpotent, right? This mechanism, this machinery will work. So in a quantum field theory, you're going to start with some classical action with BRST symmetry, gauge fix it with this sort of BRST technology. Then you're going to quantize your theory. And all you need to make sure of is this quantization preserves the BRST symmetry. If you guarantee that, then the whole gauge fixing procedure will work in the quantum theory too. Okay. So the way this is often introduced in the textbooks is that you sort of start from an expression like this, with some gauge fixing constraints and some Jacobian. You rewrite it in terms of ghosts, and then you observe this miraculous appearance of this BRST symmetry. But anyway. Okay. So I'm sorry this was a bit technical, but this gives us the tools that we need to gauge fixed string theory.
So can you just explain again the relationship between this equation and that picture that you've drawn?
So I'm saying that this integral is essentially doing an integral over these slice. So it's an integral over the gauge orbits. So let me say it properly. So I'm just saying that this integral, if you put, it's going to give you essentially an integral over the manifold modulo the group over the gauge orbits.
And how do I see that from the equation?
Well, I'm just saying, you see, the function typically will intersect your gauge orbit in a certain number of times, say once or some integer. So this, well, I mean, one thing you can do is to just do the integral over b and b, right? And then this becomes an integral over, I mean, you can integrate over all the ghosts. You just get the integral over dx, and then the delta of f, and then the df's. So this just gives you an integral over these slice, weighted by a Jacobian factor that makes sure that each intersection with the orbit is counted once.
So if we put the action into the exponential as well, then we'd get the correlation function of those operators.
That's right. I'm perfectly free to, if I have that's correct. Here I could add any s of x. When is that this is going to, when does this preserve BRST symmetry? That's right. The variation of S is just the vector field acting S. So as long as S is gauge invariant, it's just integrating e to the s, e to the s over the space of orbits.
Can you do BRST with any group, any gauge group, or does it have to be compact?
I think you can do it with any gauge group. I don't see why that would be a problem. Even if these orbits are non-compact, as long as your slice hits them only a finite number of times, it should be fine. I mean, after all, we are going to use it for non-compact groups, like the group of wild transformations. Those are definitely not compact groups because they're just multiplying by scale. Any more questions? Actually, I'm curious, did you encounter BRST quantization for electromagnetism or in the QFT course? I see. So this could be a good time to pick the Peskin and Schroeder or whatever other textbook you like for quantum field theory and go check BRST quantization there. Okay. So there's one last thing I wanted to mention, that is sometimes it's not convenient to define submanifolds by a bunch of equations. Sometimes it's more useful to define them parametrically. Right? If I want to describe a circle in the plane, I can use the equation x squared plus y squared equal to 1. But I could also decide that I want to say, no, I want to define it as x equal to sine of theta and y equal to cosine of theta, as theta varies from 0 to 2 pi. Right? So what that means is that somehow you might want to include some parameters in these equations. Describe the manifold as these parameters vary. So if you do something like that, you need your integral to also include an integral over the parameters. So there is a variant where here your gauge fixing functions also depends on the parameters. And you can add some sort of ghosts for the parameters. So here you're going to get an extra term. Everything works in the same way. This will be useful for us because this is useful every time the gauge fixing conditions involve some space of possible solutions. So let's look at the case of string theory. We said that locally on the Riemann surface, we can gauge fix the metric to be flat using the diffeomorphisms and wild symmetry. But we know that we cannot do it globally on the whole surface. All we can do is to say the metric equals some reference metric labeled by a complex structure on the surface. So if I want to write the gauge fixing equation in string theory, I cannot write HAB equal to del AB, right? All I can do is to say HAB equals some reference HAB, which is a function of my complex structure parameters. This is not so bad because there is a finite dimensional space of complex structures for the surface. Right? Okay. So when we do the path integral of string theory, we'll have to include these parameters. So let's try to write something down. We want an integral over our scalar fields that describe the position in space-time, an integral over the matrix. Then we want to have ghosts for the diffeomorphisms. These are going to be vector fields on the surface because diffeomorphisms are vector fields on the surface. So remember, we have one C ghost for every direction in my Lie algebra. So if I look at the Lie algebra of diffeomorphisms, I'll have a ghost for every diffeomorphism. So my ghosts are going to be vector fields on my surface. That's why I write the path integral. There is an infinite dimensional set of ghosts, which are functions on the surface into the tangent bundle. Then I need B ghosts. Well, I need also a C ghost for the wild transformation. It's just a function on my surface. I need ghosts associated to this gauge fixing. And their bosonic superpartners. Okay. I have an action, which is just the action for the axis, plus the BRST variation of this, which means BAB, HAB minus H hat AB of mu. And I need to include, right, an integral over the possible parameters or the possible space of complex structures, together with some partners. But these are going to be finite dimensional integrals because there is a finite dimensional space of complex structures. Okay, so do you have any questions? Yes.
So if you put there something that goes for the D field group, you should have a structure of Lie algebra.
Yes, that's correct.
Right. So what is the what is the Lie algebra, for example, for the D fields?
So let's take, so the homomorphism on my surface is something like this, right? A vector field on the surface. The commutator of two diffeomorphisms is just the Lie bracket of these vector fields. So my structure constants sort of take two vector fields and give me another vector field.
But for example, like a rotation is a D field, and also a translation is a D field. But translations commute and rotations don't.
That's right, because the Lie bracket between two translations vanishes.
So you have all of that included, just...
Right, so I have not written this BRST transformations. I'm going to write them in a moment. But essentially what you have here is going to be, so here you get the commutator of the two transformations. So here I'm going to essentially get something like the Poisson bracket between two C's.
Yeah, please.
I'll write it in a moment. Yes?
So what, like, okay, I feel like some of these things overlap. Like, what is the integral over?
So these are the original degrees of freedom.
Okay.
So this is analogous to dx.
Okay.
These are the ghosts for diffeomorphisms and Weyl symmetry.
Okay, so they just relate
So
to manifold.
they're analogous to this.
Okay.
Analogous to this. And these are the gauge fixing graph.
And why do you have, so is the difference between H, A, B, and H hat, like that, the F, like we want that?
Yes, that's correct, because the equation I want to impose is that this equals to that. That's a gauge fixing condition I want to impose. It's a very simple gauge fixing condition because it's nice, linear, has no derivatives. Right? It's actually much simpler than the gauge fixing conditions that you might encounter in electromagnetism, which have derivatives. And the fact that it's linear will ultimately allow us to integrate away and get rid of a lot of these degrees of freedom. So let's spell this out, right? So I have two terms. One term is capital B, right? And the other term, well, sorry, before I spell it out, I need to write down the BRST symmetry. So let me do that. So what's going to be the BRST transformation of X? Any guess? How does a diffeomorphism act on X? That's right. I need to act with this as a Lie derivative by this vector field. So just CA, I should probably put it up, dA x mu. Also, I mean, notice that Weyl transformations do not act on X, so I don't need to put a contribution from the ghost of Weyl transformation here. How does Q act on the metric? How does the diffeomorphism act on the metric? the combination HAB, DXA, DUA, DUB is invariant under diffeomorphisms. But H itself transforms, right? The metric transforms under diffeomorphism. How does it transform? Did you do some general relativity?
Two factors of the Jacobian.
Right, or infinitesimally.
Oh, you add the
By the A CB plus the BCA. Where I lower the indices using the metric itself. And also I need a contribution from the Weil factor. Right, the Weil transformations rescale the metric. And now I need to write down transformations of, well, transformation of the B ghost is very simple. That. Transformation of the C's involves the Poisson, the commutation of true transformation. So the Weil group is abelian. I just get 0 here. Well, it's abelian, but it does not commute with diffeomorphisms. Right? You can easily convince yourself that if the diffeomorphism acts, the commutator of a diffeomorphism in a Weil transformation is the vector field acting on the Weil parameter. So here I get something analogous to that. And if I look at diffeomorphisms, I get something like this: CA, DA, CB, DB, CA minus, well, actually, yeah, you get just I wonder if I'm forgetting a term. And there is minus CA, DB, CB. And remember, I think this is correct. Anyway, you can just ask yourself out what's the commutator of two diffeomorphisms. I hope I got that right.
Conditions are like from consistency.
Oh, that's right. You can also just ask for this to square to 0. I hope I can't remember if you had this term. Just a moment. I had them written down here. No, sorry. There is just. I think it's just this. Anyway, check me. Check that these are in this square into 0. And really, whenever I write derivatives of vectors, I really should write covariant derivatives. Yeah, that was the point. These are covariant derivatives. Okay. Okay. So now you can evaluate the gauge fixing action. So let's compute Q of BAB, HAB minus H hat AB of mu. Right? I have a term where Q acts on B. So this term would just have the effect of giving us a gigantic delta function setting the metric to the reference metric. Then there is a term where Q acts on H. So I use this expression. And I guess essentially something like that. So I get an action for the ghosts, just a derivative. So these ghosts are going to be interesting, right? You don't want to integrate them away because otherwise you get some horrid determinant of a differential operator. So these ghosts we're going to keep by integrating them away. There is also an extra term that comes from the wild transform, the wild ghost. So this has no derivative. So ultimately, we're just going to integrate away the wild ghost as the price of making this be traceless. So this wild ghost just behaves like a Lagrange multiplier, which sets B to be traceless. And finally, there is a term where this Q acts here. You get a derivative of the metric, of the reference metric, with respect to whatever parameters you use for parameterizing your complex structure deformations. And then the corresponding ghosts. I should probably give them some symbol not to confuse them. Okay. So let's simplify things now. Do you have any questions about this expression? I'm just applying these rules in a straightforward way. So I'm going to integrate away a bunch of fields. Capital B, the metric itself, the trace of B, the wild ghosts, and even the C hat auxiliary guys. So what do I get? I'm left with an integral over the x's, an integral over the traceless part of B. Let me just still denote it as B, AB, but let's remember that it's traceless now. Over the ghosts for the diffeomorphisms, and over the space of complex structures. I have an action, which is the standard action for the scalar fields evaluated on the reference metric. I have an action for the ghosts, this part. Still evaluated on the reference metric. And then the only thing that is left is when I integrate away the C hats, I end up pulling down a certain number of factors from the action that give me a measure for the mu's. So there is a product of these objects. And actually, let me just put the mu's here. So I got a nice measure. So this part, right, is a correlation function on the Riemann surface, or on the surface of some field theory of scalars and ghosts. And the insertions of, I have some insertions of B fields which build up the measure of integration for integrating with the space of complex structures. So I first need to do a calculation on a surface with a given complex structure. It's called the Riemann surface. That's why I keep saying Riemann surface. Riemann surface is a surface equipped with a complex structure. And then you integrate over the space of complex structures. This is what we wanted to get. A word of caution, when you integrate away fields, right, you need to replace them by their. So let's look at equations of motion. What happens when I integrate away h? When I integrate away h, I get an equation of motion which receives a contribution from the variation of the metric with respect of the action with respect to the metric, and from this term. So this essentially sets capital B to be equal to the variation of the metric with respect of the variation of the action with respect to the metric. So wherever we had B, we're going to have to replace it with a stress tensor. Because the equation of motion, because it was essentially, the integral of the metric essentially gives you a delta function that sets the capital B to the stress tensor.
Could you explain that point again?
Yes, I'm just saying, let's see. So I could explain this in two ways. So I integrated away a bunch of fields. Hopefully the symmetry is still there. But the symmetries involve some of the fields I integrated away. So I can at least try to replace them with the values. I mean, I had a quadratic action. I integrated away some fields with quadratic action. I should be able to just replace them by the extremum. To be sure that this works, you really need to check that Q still squares to 0 with this definition. It takes a little bit of work, but it does work. But it works in a way that is a little bit different from the way it worked before. So when you start from some nice action like this and you integrate away some stuff, your Q symmetry is still there, but it only squares to 0 on shell. So it only squares to 0 up to the equations of motion. Instead of working here, which is complicated, I can give you an example in the sort of simpler setup, which shows you most of what you need. Suppose I deform the action by a B squared term. I can do that because B squared is exact. This is essentially meaning that I put here something like BB. Once I do that, I can integrate away, I can try integrating away capital B again. And I get something nice, something like e to the minus f squared plus BA IF. It just so happened that this Gaussian integral, which now is spread over the whole manifold instead of being localized over the submanifold, still gives you the same answer as the integral over the submanifold. There is this nice notion of Poincare duality where you trade integral on a submanifold by insertions of a form. This form starts its life as a delta function, but you can deform it to something that is nice and smooth just by shifting by sort of exact amounts. And this is what we're doing here. So here everything works. But now the transformation of B is F. And if I try to check that the action is invariant, it still works. But when I do Q square of B, I get BF C. This only vanishes because the equations of motion of B set dF to 0. So Q squared does not vanish anymore. It's proportional to the equations of motion. Is this a problem? Well, in an integral like this, it would actually be quite a problem. I mean, equations of motion just do not hold in correlation functions if I just have an integral. They hold up to total derivatives and mass. On the other hand, if this was a quantum field theory, the situation is not that bad, because equations of motion in quantum field theory correlation functions hold away from the location of other operators. So as long as you're studying correlation functions of operators at different locations in space-time, you still have that. There are no problems, no big problems. There is a risk of problems when you look at operators which are integrated over space-time, because then they're going to hit other operators. For example, if you try to deform the action, deforming the action means that you're adding an integral of something to exact over the whole space-time. This can hit other operators and give you troubles. So it's not true anymore that to deform the action, you just shift it by something to exact. You need to be a bit more careful. What's going on is that because the definition of Q depends on your action, as you deform your action, as you start deforming your action, your definition of Q also changes. Maybe even the definition of the operators changes because, for example, imagine because the definition of Q closed operator changes if you change the definition of Q. So as you try to modify your action, you sort of need to things become nonlinear. Here, so in this setup where the symmetry was holding off shell, I could literally add to my action any Q exact term and get another valid action. So the space of good actions was a linear space in the space of all actions. Once I go off shell, the space of good actions is some nonlinear space in the space of all actions. And you can see it, right? This is a nonlinear expression. If I change f, if I try to change f, this changes by a nonlinear amount. If I try to write a generic action, where I write a v here, I'll discover that this is symmetric only if del v is f del f. So if v is f squared. So I get a nonlinear constraint on the action that makes it BRST symmetric. The reason I'm stressing this point is because it will be very important next week. Next week we're going to ask a question. We're going to ask the question, can I make a string move consistently in a curved space-time? So we're going to write down an action for a string coupled to a background metric. We're going to ask, is this action BRST invariant? And it turns out that it's only BRST invariant if some constraints, if this metric satisfies some constraints. These are nonlinear constraints. They are called Einstein equations. So when we study a string moving in the background metric, we'll discover this metric has to satisfy Einstein's equations. Einstein's equations are nonlinear, so to reproduce that result, you definitely need to be in a setup like this rather than a setup like that. So I'm sorry for the parentheses, but I think it's a point that is worth remembering later on. Okay, so going back here, once we put the symmetries, once we integrate away all these fields, the BRST symmetry holds on shell, and you need to be careful whenever we have collision of operators or other situations like that. So there is the risk of so-called BRST anomalies, and they typically have a very physical meaning.
Is that the same as a gauge anomaly?
It could be. So BRST anomalies can be a variety of things. Sometimes they might tell you we're trying to gauge a symmetry which is not anomalous, you're doing something bad. But sometimes are milder things. They're trying to tell you things like, careful, you're trying to deform your action by some amount, but you need to do it in a nonlinear way. Okay, I think we're done. And I suggest for you an exercise to actually check that Q square of x vanishes in this definition, or Q square of the various. Well, now you don't need this anymore, right? Because the metric is gone. You don't need this. You only need this, and this. Remember, this is the total stress tensor. It will still include contributions both from the action of the X's and the action of the ghosts. One last piece of information I wanted to say, if you look at integrals like that, it's interesting to count the number of C's and B's that you have in the measure. Because the action pairs up B's and C's. So the difference in the number of C's and number of B's in the measure tells you how many C's you need in your observables. Right? Here, if I wanted to integrate a form on a submanifold dimension K, I needed to have K, a form of degree K. So the Gauss number symmetry is a symmetry that gives charge 1 to C and minus 1 to B. And it's sort of analogous to measuring the degree of forms. So it's a useful thing to have available. And so let me just define the current for the Gauss number symmetry, which is just BC. So this is a current which will give charge 1 to the C's and minus 1 to the B's. And also, I'm sorry, yes, that's right. So I should put some indices, so it's going to be something like that. Okay, I think this is it. Right, I should probably just write down the stress tensor for the ghosts in holomorphic gauge. No, yeah, there was something I should say. So I said there is a symmetric traceless B and there is a C. When you write when you work in complex coordinates, that means that we have a CS, which I'll call just C, CS bar, which I'll call C bar. I have a BSS, I'll call B, and a BS bar as bar, which I'll call B bar. Okay, just for notation. And in this notation, this is just BC, and there is a J bar, which is B bar, C bar. There is a stress tensor for the ghosts, which is something like C del B plus 2 del C B, and a similar holomorphic part of the stress tensor. So these are just expressions we're going to use. They can be derived in a pretty straightforward way, just writing down the ghost action and varying it with respect to the metric. But it's an exercise we need to do. Also, just like I can't resist pointing out, so this tells you that the stress tensor is Q exact. So in particular, correlation functions involving the stress tensor will give you 0. So you can see that this BRST formalism in particular is imposing the constraint that the stress tensor vanishes, which is the classical constraint. So all of this formalism can be thought of as a way to consistently set the stress tensor to 0 in our correlation functions. Okay. Any questions? I know this was painful, and there was a lot of information packed in just one lecture. At the end, we're just going to use a little bit of info, just this final result. These expressions are pretty much all that we will need for the rest of the lectures. You can take these expressions as an axiomatic definition of your string theory and forget about their derivation. But it's good to know where do they come from. Because otherwise it always looks like there is some oracle telling you, oh, this is a B insertion that you need to put there. Here we need this number of B's, or and so on and so forth. Okay.